My friends, it's just so wonderful to see you all here. It's so wonderful for us to come together as a community to honor Joe. And actually, I thought that the best way in which we could honor Joe was to engage in something that he deeply loved, which is talking about science and especially his science. And we have three amazing guides that are going to take us to sample a bit of Joe's sort of unending curiosity. And the guides are Fred, Larry, Bloom, and Raphael, who's who's going to join us online. My job is going to be to be sort of the timekeeper, but I don't want to take any more from what we are here for, which is enjoying Joe, in a way, teaching us one more time what he was excited about. So, Fred, why don't you take the floor?
Thanks. It's a privilege to be here to honor Joe and, in a sense, to honor you. I'm going to talk about 1984, not the dystopian world that George Orwell accurately predicted, but the productive world of Joe Halpern. In August of '84, he presented a paper work done with Yoram Moses at Podsy. It was a revolutionary paper, and it discussed the use of knowledge and common knowledge for distributed systems. It's going to be one of the high points, but only one of the high points of Joe's intellectual legacy. But he did other things in 1984 too. And I thought it might be interesting for you to see those two, and in that way get an idea for the scope of activities that Joe has been involved in. And I also thought it'd be useful for you to see the context in which this work was done. So to remind you, he got his PhD in '81 from Harvard. He had a thesis advisor from MIT, Albert Meyer, who at the time was one of the top Popple people in the nation, and Sachs, a mathematician. And the thesis was on axiomatic definitions of programming languages, which in Cornell speak says this was squarely a 6110 thesis. This was a programming languages theory. In '82, he joined the research group at IBM Almaden. IBM research had two theory groups. One was at Yorktown, and actually Dexter comes from there. And the other was in Almaden, and I'll say, or San Jose in those days. And then in '96, we succeeded in attracting him to the faculty at Cornell. We hired him because we wanted to grow in AI. He was seen at that time as squarely in AI, but he had a background and perspective in doing things rigorously. And so it was a pretty gradual transition for the department to have somebody like that building up our AI group. This was the second time the department tried to build up an AI group. And this time, as you see by looking around, it's clearly worked quite well. So what were the hot issues of the day when Joe was in graduate school and finishing? And it was, how do you reason about programs? How do you establish that a program is going to do what it's supposed to do? And there were many proposals around, and two that had a good deal of traction was the use of this force-style logic, and I'll return to that in a minute, and the other was temporal logic. Amir Pinwelli had suggested it. He won a Turing Award for this eventually. And when he suggested it, he suggested that formulas be interpreted with respect to sets of traces. Each trace corresponded to an execution of a program. Now, another way to represent that set would have been as a tree, where every path in the tree from the root to a leaf corresponded to an element of the set. And the interpretation that Amir was using was called linear time. And the interpretation that I just described with respect to trees was called branching time. And these are two things that philosophers had looked at in connection with temporal logic. Temporal logic was a branch of philosophy and logic long before it entered computer science. Well, the advantage of using trees was not lost on a PhD student at Harvard, Alan Emerson, who was interested not in proving theorems, but in enumerating over possibilities. That's known today as model checking. And it was better to model check a tree than to model check this big set of traces. And so Alan was looking into how do you model check temporal formulas with respect to these trees. And that caused him and his advisor, he dragged his advisor into it. His advisor was Ed Clark, to investigate this other logic. And this other logic sometimes and meant possibly, and in linear time logic sometimes didn't mean possibly. And so there was this spate of papers as the field tried to decide which was, quote, better. Lamport was a big proponent of the linear time semantics, and he threw the gauntlet down and wrote a paper in Popple 90 called Sometimes or Sometimes Not Never. And that is a perfectly sensible statement if you interpret sometimes, never, and not in the logical sense of temporal logic. And the rebuttal was a paper by Halpern and Emerson, which appeared in '83. Some of you know I talk about aspiring to write the first paper, the best paper, or the last paper. This was the last paper, and it sketched everything out. As an aside, Emerson realized that you needed to do model checking on finite state stuff. He looked at doing it on synchronization code because everybody was having trouble writing synchronization, and synchronization code was easy to get wrong, and it was finite state. They eventually, he and Ed Clark decided to try it out on hardware, which was finite state, and model checking for circuits was born in that way, and Emerson and Clark eventually got Turing Awards for that work. So Joe worked on that, but that was 1983, and remember, I wanted to talk about 1980. So let's talk about the work on axiomatic logics that Joe did before. So in '69, Tony Hoare proposed this new idea that you could write logical formulas that had the program in the formula and had a logical assertions that describe possible starting states and the resulting finished states. And that was this PSQ with the brackets around the S was the syntax that it was. So the program was the comment. So that's changed since then. And the question is what you can prove with this. And what you can prove is a question about what the P and the Q can say. And it's a question about what can be an S, what can be a program. So Cook in '74 showed that what you can prove correctness for these logics is, first of all, if you prove something you want it to hold, so that's soundness. And there's no hope of completeness for these logics because if the assertions talk about arithmetic, first order stuff, which is what you want to talk about for a program that does something interesting, then there's no complete way of reasoning about those assertions. So adding the program statements doesn't make your life any harder. Cook came up with this cool way of talking about completeness for programming logics that were relative to completeness for the assertion language. And in addition, there was Ed Clark, remember, at Harvard. Ed Clark's PhD thesis at Cornell under Bob Constable had been that it's hopeless, that a programming language that was block structured, had recursive procedure, could have procedure names as parameters, which in those days was fashionable, had global variables and internal procedures. You can't axiomatize that using Hoare logic. So that any rich language was going to be hopeless. And Joe came along in 1984, building on his collaboration and showed actually if you had an expressive enough assertion language, it was higher order, then you could accentize it. So this was the thing that said it wasn't a hopeless exercise. We could handle arbitrarily complicated programming languages. And to give you a sense of how this works, piece SP, so pick an assertion about the state, run any program S and hope that P holds again. Well, if S doesn't have any assignment statements that name the variables in P, you would expect that P should hold afterwards if the program terminates when P held before. And it turns out that's not true. If S has calls to procedures and the procedures have global variables in them, then the global variables are not apparent in S, and the global variable assignments could have been in P. So that's why that SP is not sound in a language where there are global variables in recursion. And what Joe said is he could invent an assertion language in which you could talk about the things that S affects. And this was the idea of covering assertion that he invented. And those of you who are doing programming logics today know that we're all looking at something called separation logic. And separation logic really is an approach, a packaging of this kind of thing, although people don't talk about it then. So he made a pretty interesting innovation then in core-style logics. He was at IBM San Jose, and the research group there was somewhat, it was a theory group, so they could, quote, do whatever they wanted, but they understood they were supposed to support the company. IBM was a big manufacturer of mainframes. It was important to them for mainframes to be adopted by big companies, and they saw their success route as through databases. So IBM is interested in companies having databases. In 1970, COD invented the idea of relational databases. COD was at the San Jose Research Lab. So there was very much a group interested in databases. And Joe was there in service of that group. At the same time, around then, transition going on from networks. So think of a network as a distributed system where you care more about the wires than the boxes. To distributed systems, that's a network where you don't care about the wires, but you care about the boxes. So distributed systems became interesting because microprocessors and mini computers became available. So an academic actually could build a distributed system. So on the one hand, there's this interest in networks that's transitioning to distributed systems. Xerox saw its future in putting computers on everybody's desk and replacing word processors. So Xerox was also interested in this. So IBM's worried about databases. Xerox is worried about distributed systems. And one of the people working at Xerox as an intern from Stanford was a guy named Marzullo. Marzullo invented a way to synchronize the clocks at all the processors in a distributed system. That's what you needed to do. Marzullo's thesis advisor was Susan Nowicki. Susan Nowicki is a Cornell PhD. Marzullo is Alvisi's thesis advisor. He left before Alvisi finished, but for the most part, that was where Alvisi came from. Okay, so we have all this interested in coordinating different units. Marzullo is looking at clocks, and his view of clocks were they were intervals. The time was someplace in there, and as time went on, the interval got bigger because the clocks were drifting. The final ingredient in this picture was in 1973, OPEC created an oil embargo. And we in the United States were very worried about having enough fuel oil to run cars and to run airplanes. The FAA appreciated this and commissioned a bunch of research on airplanes that were dynamically unstable. That is, you had to constantly be moving the controls to keep them flat. Most airplanes up until then used a lot more fuel, but they were stable. If you took your hands off the wheel, it would just fly straight. This one needed constant manipulation. And you couldn't expect somebody flying an 8-hour jet flight to be constantly doing this. So they understood you would put a computer in the plane, the pilot would send signals to the computer would control the surfaces, the control surfaces all the time. But to put something on an airplane, it has to be reliable. And the FAA has high standards for reliability. And so the FAA wrote a couple of grants to build a reliable computer to fly an airplane. The name of the computer that was built at SRI was called SIFT. And they discovered that if you want to do replication, you have to have the inputs agreed upon at the replicas. And that was the birth of the Byzantine generals problem. So distributed systems, the oil embargo is where Byzantine generals are. And that's where the world is. But agreement on time is different than agreement on a value because time keeps advancing. So you should look at time as a function. A clock is a function from real time to clock time. And you can't just send a clock through the network, right? You can send values through the network. So the problem was, how do you synchronize clocks when some of the component processors are acting faulty, which means exhibiting Byzantine behavior? And it was PODC 83 where Marzullo published his algorithm. And in rebuttal, in PODC 84, people started talking about Byzantine clock synchronization. As an aside, Marzullo's algorithm was running the internet up until about a year ago. So that was a thesis that had a long life. So the challenge, which was articulated at PODC 84, was how do you do synchronization? That is, keep the two clocks from drifting apart. You assume their rates were off by at most rho. And how do you make sure the clocks at two different processors always were within delta? And if you think about this problem, it's just a question of taking a continuous function of real time and building a piecewise continuous function of real time and periodically adjusting the clock. And so this resynchronization is the obvious high-level way to do this. And in order to do resynchronization, you would need to solve three problems. One was, when does P resynchronize? And it's not going to happen at the same time at different processors, because then the clocks would have been synchronized. You don't need to do anything. Second, how much do you adjust P to bring it in line with the others, which are, by the way, adjusting also? And the third thing is, how do you spread the adjustment out? You can't have this discontinuous time. You need to kind of gradually spread it out over the next time. So this is the canonical recipe for clock synchronization. So Marzullo in 83 shows an algorithm which isn't very Byzantine fault tolerant, ends up being the one everybody uses, but in retaliation, the Byzantine crowd says, no, we're going to show you how to do Byzantine clock synchronization. And so PODC 84 had first a paper by Les Lamport and Mike Millier-Smith. Les Lamport is the guy behind Byzantine agreement. So he's an author of that paper. And he, with Mike, show two algorithms for doing Byzantine clock synchronization. One is the, quote, obvious one in retrospect. It says basically, when your clock reads time t, or ET for some E, so every epoch, you go and read all the other clocks, then you take an average of the values and set your clock that way. As long as everybody's taking an average of more or less the same things, and the averages don't get upset if maybe T of those values are out of this world because they're from faulty clocks, say one thing to one request and another thing to another, then they'll come together. So that's the birth of a family of algorithms known as approximate agreement algorithms, and PODC is then inundated with those for a while. And the second approach that these guys suggest is, let's just take a vanilla Byzantine agreement algorithm, and instead of agreeing on values, let's agree on clocks. And so they just took their agreement algorithm and showed how to send a clock through the network, right? And now Byzantine agreement algorithms make copies of values and send them many ways. Well, there was a third approach, and it also was described at PODC 84, and it's the one that Joe was involved in. And the idea of Joe's algorithm, which I've nicknamed fireworks, is when your clock reaches the right number, you blow off some fireworks and everybody sees it. And based on seeing the fireworks, they reset their clocks. In particular, the F plus first firework had to have been preceded by a firework from a good processor if they're at most F faulty. And they worked out the math to show the way you send fireworks is you send a message out every outgoing edge, and everybody who receives a message sends it out, so it kind of diffuses. So they worked out the details, and they ended up having an algorithm that would tolerate up to F fault with F plus one processors, whereas all the Byzantine-based stuff that Lamport had suggested was 2F plus one or 3F plus one. So it was much more fault tolerant. It was a novel approach because it's based on simultaneity, which you will see shortly is important. That was kind of new. And a guy named Sam Tuig with a student Srikant then was able to show a small extension that established this was optimal. Tuig was a faculty member at Cornell when he did this. So we now were, by the way, an estate since Marzullo joined the faculty here too. We had a majority of the authors of clock synchronization algorithms on the faculty. So 84, remember, is the year that besides all this other stuff was when Joe published his knowledge with Yoram. And what it does is it gives another epistemic logic. So he knew a lot about temporal logic for talking about the metaphors that are interesting in distributed systems. If you talk to an untrained programmer who's programming a distributed system, he'll talk about I says this, and then you gets this message, and you believes that I says blah, 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 and there'll be I's and U's, and it'll be very anthropomorphic. Well, Joe just converted that to logic, and he gave a way to talk about what an individual, quote, believed, which meant a predicate that held that the individual could believe was true, what a group could believe, and most importantly, so everyone could believe something, that was E, and C, common knowledge, which was a fact was common knowledge if it was true, everyone believed it, everyone believed that everyone believed it, everyone believed that everyone believed that, and so on. And common knowledge was what those agreement algorithms were all about. And it's also what those commit algorithms were all about. So distributed computing had this big family of algorithms, but no uniform way to talk. So this was now a way to talk about it. And inventing a language is always an interesting, important contribution. But what came with this language was a bunch of insights about how to change from one level of knowledge to another. Right? So common knowledge implies everyone knowledge, which implies implicit knowledge and so on. But there were some theorems that said you can't get common knowledge if some of the links are faulty. Right? Hey, that just blows it out of the water. That's just the same thing as you can't solve the halting problem, right? Because most systems have faulty links. He also proved with Yoram that simultaneity is required for achieving common knowledge. So this is a pretty bleak picture. We now have a logic and logical basis to decide we can't solve a lot of important problems. And they went on then to look at some variations of common knowledge. Epsilon common knowledge, which was if you can't look at all the processors too close together in time, which is a realistic assumption, if you had to look at them epsilon apart, then it wouldn't have been real common knowledge, but it would be epsilon common knowledge, and that's good enough. It's indistinguishable from common knowledge to the observers in the system. And he invented something called eventual common knowledge, which corresponds to what happens in an asynchronous system. And that corresponds to a model that's often used in distributed computing where you don't want to assume message bounds and you think of things. So they built for us a language and a logic and a way to reason about it. And the next step was going to be to use this as the language and derive protocols from it. So you can imagine writing down a formula with C's and K's, and then systematically ending up with a code for a distributed protocol. And they worked on this, and many people in the field worked on this, and nobody got very far. So it's an open problem. It says it was a hard problem, and I know some of you are PhD students. So if you look back at 1984 and you go look up DPLP, you'll discover that Joe published in AAAI, Fox, Podsy, Popple, and Stock. I think for each of your areas, you each would aspire to get one paper in one of those. You're looking at 9 papers. He published 2 others. So that year he published 11 papers in super competitive venues. And he spanned, I'm not a big person for proxy measures, he spanned contributions in 6110, 6410, and epistemic stuff, which also is covered in philosophy here at Cornell. So it is an amazing legacy, and this is just 1 year.
No. Oh, I am next, am I not? Yes.
And you should be on already there.
I'm here, but I can't share. The sharing is turned off.
Rafael, no. It's going to be Larry now.
I wish that was
Yeah.
it's PhD. That's what it is.
So solid change slides.
It was. You could be like, I did my time.
Shut it.
Construct.
With the first one.
Okay, it's my pleasure to talk about Joe Halpern, game theorist. Now, we know that Joe has contributed, as we've already heard, to many areas of computer science. Joe has lots of papers that actually a lot of research whose audience extends beyond computer science into the larger world of game theory. Joe even has 2 papers on monetary theory for any economist who might be in the language of computer science, these are called script systems. But I believe actually with some of the research going on at the Federal Reserve, at the Board of Governors today, they should be interested in this paper, in these 2 papers. But I'm not going to talk about that. I want to talk about Joe's many contributions to this, to computer science. And just very quickly, I want to show you that he has a lot of papers. I'm sorry, he has a lot of papers in game theory, right? He actually has, by my count, 51 papers on the topic of game theory. And this is applying my filter. My filter is, actually it's not 50, yeah, it is 51. And my filter is not that anything remotely related to game theory, but papers that game theorists who are not computer scientists could read and appreciate. And that alone comes to 51. And of course, actually, game theory really should include essentially almost anything having to do with multi-agent or distributed systems papers, anything having to do about reasoning in groups. And so by that count, it would be just an enormous list. So I want to talk about, to my criteria, some of the things that Joe has done. His work in game theory, I put it into 4 subdivisions. The first subdivision I call the foundations of game theory. So throughout his career, as we've already heard, Joe has thought a lot about the epistemic foundations of reasoning. He's thought about the epistemic of decisions. And so, of course, this spills over into game theory, which game theory has actually been described by Robert Aumann as the investigation of interactive rationality. Phrased that way, you all know this is right up Joe's alley, right? And so it's not surprising that Joe found his way to game theory very early on. He has written on, within the area that I call foundations, he's written on the epistemic considerations in game theory, representations of uncertainty within games, analysis and interpretation of existing non-cooperative equilibrium concepts, and also the real fundamental question, which is how do we actually represent games? So that's just one area. Second area has to do with resource-bounded game theory. Joe has been very interested over the course of his career, and I will also say in the decision theory class that Joe and I have co-taught off and on for over 20 years. Joe's been very interested in resource-bounded reasoning and consequently in resource-bounded game theory as well. By resource-bounded, I don't mean the fact that finding the set of Nash equilibria for a game is a computationally hard problem. I mean the fact that the agents within the game have limited cognitive capacity, resource-bounded in that way, and how that changes what we know about what should happen in games. A third area, yeah, there it is. A third area is something that I'm going to be talking about a little bit more in just a moment. This has to do with, well, actually, this area I'm not going to be talking about. I'm going to be talking about the first area a little bit. But a third area has to do with new equilibrium concepts. There is a lot that's wrong with the fundamental concept of equilibrium concept in non-cooperative games, which is called Nash equilibrium. So there's work to do to figure out things which are better. There are also game theoretic environments in which the non-cooperative formulation doesn't really precisely fit into. People who perhaps reason in different ways. People who are, for example, people who are nice to other people. Game theory is not really about that, right? Another thing is that Joe has been interested in is games in which people are unaware, right, of the details of the game that they're playing. Unawareness is a hot topic in game theory. Being unaware of the strategic situation, unaware of the capacities of your opponents, and so on and so forth. And the work that you see in the game theory literature kind of reaches back to a 1995 paper of Modica and Rusticchini, for those of you who might want to track it down. But of course, the original unawareness paper, to the best of my knowledge, was written by Joe and Ron Fagan. Was that in 1988, I think? And of course, the game theorists have subsequently discovered this paper and drawn a lot from it. Finally, Joe has also been interested in applications of game theory. So I can't think of very many people who are making an entire career out of game theory who have this span, this breadth of interest and this breadth of significant work in game theory. So he's done some very interesting work on voting, on the concept of liquid democracy. My favorite papers are those on, which is not to say that there's anything wrong with any of the others, but the papers that are closest to my heart as an economist here are those papers on script systems and how do you get people to take money, essentially. So there's a lot here, and I'm not going to talk any more about any of these, but again, this is a tremendous span of research. Finally, there's a bunch of papers that I call other, and included on this list are a number of survey talks. In preparing this talk, I looked at several of these. They're all fascinating, and there's a lot to learn from. I particularly like solution concepts for the 21st century, since now that we're there, it's a good thing to think about. His survey of what computer science has to contribute to game theory and perhaps what computer science might learn from game theory. I think those last two papers on the right are well worth the reading, in particular graduate students who might be interested in diving into some of this. it was a little hard to choose something to talk about because I wanted to find a topic that I knew a lot about, and also a topic that Joe's frequent co-author, Raphael Pass, who's speaking in a moment, didn't know more than I do. And there's not a lot to choose from here. So I want to talk about Joe's work on what are called refinements of Nash equilibrium. Now, there's not a lot of time, enough time to explain what Joe did, but I want to explain what the problem is as an exemplar of the kinds of things that Joe is interested in with foundations of game theory. And then just mention very quickly, really in one or two sentences, what two particular papers that I like a lot about what Joe did are about. There's another reason for choosing this topic, and that is that this topic and Joe's comments on a paper, that I wrote were the subject of the very first conversation that I had when I bumped into Joe not long after he arrived at Cornell. And was that 1995? Yeah. So after I had that conversation, I thought, wow, this is a guy I have to know. And fortunately, I was able to do that. So I presume that while you're all a very literate computer science audience, you're not a very literate game theory audience. So I'm going to go very quickly to describe just enough about game theory to talk about the issues that this particular issue that interested Joe. There are two ways of representing games. One way is called the normal form. And the normal form is just a list of strategy profiles. A strategy profile is a vector, each component of which is a strategy that some player in the game will play. So you take the normal form, takes all of these profiles, and it assigns to each profile the utility, the payoff that each individual in the game gets. And that's the simplest possible description of the game. You've all seen the boxes on the right. I'm sure in top social science journals or articles, and that's a prisoner's dilemma, by the way. And so that's the normal form. The most complete description of the game is that due to Harold Kuhn. It's called the extensive form of the game. And the extensive form of a game represents a game as a tree. Every vertex in the tree belongs to a player whose move it is at that vertex. One descends or ascends, depending upon how you write it, from the root of the tree down to the terminal branches. Every edge represents a move that the player owning that vertex could make. And then finally, the dotted line between two vertices owned by a single player represents two vertices that in the course of play, the player cannot distinguish. That is to say, as is the case here in the game on the left for player two, that when player two has the opportunity to move, he does not know whether he is at vertex B or vertex C. Okay, so this is how we represent uncertainty, or one kind of uncertainty within the game. The terminal nodes are labeled with payoffs, one for each player. So these are the two representations of a game. Okay. What is Nash equilibrium? Nash equilibrium is very simply described. So simply described, it's hard to believe that there was a Nobel Prize for this. And in fact, John Nash's paper takes 1 page in PNAS to prove the existence of Nash equilibrium. John von Neumann claimed it was trivial, but he claimed everything was trivial, right? So what is the idea behind Nash equilibrium? Each player has a set of available actions, strategies within the game, also has beliefs about the play of all of the other players. Second, each player chooses the action which is best for her given her beliefs, okay? And then finally, her beliefs about the choices of others are correct. That's a very simple idea, okay? And that's Nash equilibrium. Okay. Where am I? I should actually look at my notes. All right. So we tell our students in game theory classes that the idea behind Nash equilibrium is that Nash equilibrium is a strategy profile which is self-enforcing, in the sense that if you told every player in the game, if some oracle told every player in the game what to do, right, each player would receive this recommendation, and then choose to do that, not to deviate from it and do something else on the assumption that everybody else is also going to do what the oracle said to do. All right. So self-enforcing in that no one has a sense to change their behavior if everybody else is behaving according to the description. Now, the question is Nash equilibrium really self-enforcing? And deeper question, of course, is what does self-enforcing actually mean? And my answer to that question is a paraphrase of a famous Supreme Court decision wherein Justice Potter Stewart said, I could never succeed in intelligibly describing it, but I know it when I see it. Right? And that's with self-enforcing. So here's two examples of some ways in which a game an equilibrium might not be self-enforcing. If we look at the extensive form on the left, we see that or rather the extensive form on the right. Let's start with the right. We see that player one playing left and then handing off to player two, who then chooses left in order to give both players a payoff as one, is in fact a Nash equilibrium because there's no single deviation by any player that could allow them to do better. But frankly, why would player one give away control to player two, right? Player two could screw up. Player two could be different in some way than he thinks player two is. Why not just, in fact, play to the right, and then play to the right a second time and have total control and get one for sure. Okay, so seems pretty logical that right and right is a better equilibrium than than left and left. Then look at the left game. Now we have player one. This is just a single person decision problem. But why would player one choose left twice? Because we never know. There might be some gap between intention and execution, right? So why do the complicated thing and choose big L, little l, when you could just choose R and get the same outcome? Simpler, right? Here is one more example. This game has two Nash equilibrium. One of them is middle and left, and the other one is top and right. Top and right is a controversial equilibrium. Why does player one choose to go to top? Because he fears that player two is going to go and choose right. Now, why would player two ever choose right? Should player two have the opportunity to get the move, right? This becomes even more controversial if we take that second two, the two that player number two is going to get from top, and change that, say, to a 4. Right? Now we might say that player one is choosing top because of the threat that player two has of playing right. And so I'm afraid of that threat, and so I'm therefore going to play top. But on the other hand, maybe a more thoughtful player might say, I'm going to call his bluff if he does that. I'm going to give him the opportunity to move. And I don't really think he's going to choose 0 when he could get 3. Right? So again, this is not a credible equilibrium, and simple games like this were actually the beginning of the literature on credibility. I'm going to skip that. So how do we address this problem within the context of Nash equilibrium? Reinhard Selten, another Nobel Prize winner for another almost equally simple idea, had the following idea, which is I've described on the slide here. Instead of, we're going to ask that our equilibrium strategies not just be best responses to the strategies that other people are playing, but we also want them to be best responses to some strategies, not all, but some strategies at least, that are nearby what other people are playing. So this is kind of a robustness concept. And so I've listed a number of equilibrium concepts that are called refinements of Nash equilibrium, because every perfect equilibrium, every proper equilibrium, every sequential equilibrium, every quasi-perfect equilibrium, this list goes on and on. There are things called divine equilibria. My favorite is universal divinity in signaling games. These are all attempts within the framework of Nash equilibria. All these equilibria are Nash equilibria, but they're attempts to throw out equilibria that look unreasonable just based on the structure of the game. Okay, and the way Selten implements this is to say, let us imagine a sequence of equilibria or a sequence of strategy profiles that converge to our proposed equilibrium, and then require that people are best responding not just to the limit, which is the equilibrium, but to everything in the sequence. All right. So again, this is a robustness idea. So here comes Joe. Joe asked the following question. What do perturbations have to do with rationality? Okay. This is a robustness concept. How do we fit this into rationality, right? A lot of Joe's research is really about rationality. And the answer is that you can make sense of these in terms of rationality. And you can describe a kind of expected utility maximization, right, that in fact encompasses within it this idea of robustness that's Seltman represented. And I've listed here 2 papers that Joe accomplishes this in. I'm not going to describe the papers in any great detail, but I think I'm up to my last slide. And let me tell you what that is the last slide. Let me tell you what the issue is. So here we have a game where there is an equilibrium where player A, this is disabled, and player A goes to the left, and player 2 plays right. Okay, and then there's another equilibrium where player A plays middle, and player 2 plays left. Okay, and this is the question I want to ask is, well, how do we support these as equilibria? Why do we think of these as equilibria? So the real issue is the following. If player 2 should be thinking conditional upon getting to my information set, what should I believe about where I am? Now, typically, where do we get beliefs from? We have some probability distribution. And once we have a probability distribution, if we're in some subset, we might, in fact, condition. Okay. And if, in fact, for example, player conditioning is not really an issue here because there's nothing, because there are only 2 choices in one information set. But in this information set, but for example, if player A were in fact playing M, player 2 would say, well, aha, given his strategy, I can infer, right, that I am at the node on the left, and therefore I should play 3, right? And in fact, for any beliefs that put, wrote this down so I would get it right. If player 2 or thinks that he is at the right vertex with probability at least 3/7, she would play, or he would play right, otherwise would play left. Okay. And so probability works very well for this. But what happens if player 1 plays L, because there is no probability distribution now to make any inference on from in player 2's information set? Does everybody understand the problem? Is that clear? When I start talking too fast, I kind of lose clarity. I'm not sure I have you all with me, but that's the fundamental problem in identifying good restrictions on Nash equilibrium, is to solve this problem of conditioning. What do we condition on when we have 0 probability events? And so Joe wrote that first paper, the one on, let me go back, the one on lexicographic probability, conditional probability, and non-standard probability. And in one sentence or 2 sentences, I will say that there are several different solutions to this problem. One way is to imagine having a hierarchy of beliefs, okay, and to use them lexicographically. So I maximize expected utility according to my first belief in my hierarchy of beliefs. And if I happen to be at a set, right, where the probability of reaching the set is 0, my probability distribution doesn't tell me anything about it. So I throw it away and I go to the second probability in the hierarchy, which does have support there. And then I condition on that. And I go on throughout the game. And when I get to a point where I'm at another 0 information set, I throw it away and I go to belief number 3, and so on and so on. So this is one solution. Another solution is to redefine probability. This was not done by Joe. Okay, it was suggested by a number of people, including Karl Popper back in the 30s. So these things are called Popper spaces, but way I'm familiar with it is through the Hungarian mathematician Alfred Renyi, and that is in fact to axiomatize probability in terms of conditional probability at the outset rather than regular Kolmogorov type probability, and and then require various consistency conditions among all of the conditional probabilities. And the third way is to use non-Archimedean probabilities. So what are non-Archimedean probabilities? Some of you probably know that there are many, many models of the real. There are an infinitude of models of the real numbers, some of which actually are large non-Archimedean fields, which are ordered fields which extend the real numbers, having the real numbers as a subfield. And these fields have within them numbers that are infinitesimal, which is to say smaller than any real number. And of course, also infinite numbers larger than any real numbers. And so this third idea of non-Archimedean probabilities is to say that these sets that have zero probability, they really don't have zero probability. They have infinitesimal probability. And since they have infinitesimal probability, and since infinitesimal is still positive, we can now go ahead and condition just as before. And this has particular implications for the way the decision theories that use them work. So those are the three approaches. And this one paper sorts all of this out and establishes all the relations between these different approaches. And this is really very important because there are games that we don't yet know how to talk about. And the non-Archimedean approach, which Joe is very fond of, in fact, is, I think, really the way to go. The final paper I want to mention is that Joe actually now does work on an equilibrium refinement. Sequential equilibrium, without going into any detail of what it is the equilibrium concept which is most used by applied game theorists who are studying Bayesian games. And Joe actually went backwards and provided the epistemic foundations for sequential equilibria by saying sequential equilibrium is a Nash equilibrium with a decision theory that looks like X, where X is a particular kind of non-Archimedean expected utility theory. So that's what I want to say about his work. And I want to conclude on one personal note. So many of you know, I think, that Joe and I, for many years, have taught together a course on decision theory. And in fact, Joe called me up last spring. I remember walking down Madison Avenue in New York, and I get a phone call, pick it up, and it's Joe, okay? And he says, Larry, let's do decision theory again. And I have to say, I wondered how this was going to work out, because as you know, at that time, Joe was quite ill. But of course, one has to say yes. And I was eager to teach with Joe one more time. And unfortunately, of course, we did not make it to the end of the term together. And I have been trying to learn all those things that Joe covered in the class so that I can now present them to our students. And if I have any of the students in the room, I know there's at least one, I have to apologize that I cannot do this the way that Joe did. This is obvious, but I am trying hard. And I have to say that as I prepared lecture notes and been thinking about these things, and then as coming back and looking at all these game theory papers and reading many of them, to prepare for this talk. And it wasn't just overthinking the talk. It was that I really liked these papers and wanted to read them all, many of which I hadn't read before. So I really enjoyed that. But what I realized as I was doing this, and this is a real bittersweet thing, I realized that there were many conversations that I should have had with Joe that I just never got around to having. And I have to say how much I miss this. Thank you.
Good. You have the floor, Rafael.
Thank you, Lorenzo. Can you all hear me? Excellent. So it's an honor to speak about Joe. I'm gonna try to talk about two snapshots of his immense body of research. And I wanted to start with a quote from Joe himself that he often had on his website, and he often started his talks with this quote. And this was a way that he liked to describe himself, and I think it's really perfect. So he called himself someone with a PhD in mathematics who calls himself a computer scientist who is giving a talk to economists about a subject mainly studied by philosophers, and it's very fitting. So on a high level, I feel that at least since I got to know Joe in 2006, Joe's research was all about using rigorous mathematics in order to confront ideas, the very ideas that define us as humans, and really trying to attempt to answer the almost impossible. What does it mean to know something? Why do people act in certain ways? And what does it mean to be rational or irrational? And sometimes we don't do exactly what we're supposed to do, but can we still capture that? When is it the case that our actions are causing things? What does it mean to cause something? And when they do, what was our actual intent in our actions? So these are really, really hard and foundational questions that anyone should care about. And it seems, as I said, almost impossible to capture these things with mathematics. And that's what Joe's work did. And by doing so, revolutionized distributed systems through notions like knowledge and common knowledge. And you heard some of that in talks Fred, in Fred's talk. In game theory, and you also heard about that in Larry's talk, through, again, knowledge, but also computation and notions such as awareness. And finally, revolutionize how we think about reasoning AI agents. And this is becoming a hugely important topic now. And Joe's work really laid a foundation also for how to think about agents and how agents think about each other, and in particular, things like cause, uncertainty, awareness, and intent is really crucial there. So my plan today is to just give you, as I said, two snapshots focusing a little bit on mostly about knowledge in the context of game theory, and then about reasoning AI agents in the context of cause. And the idea is just to, just like Joe, actually, he worked on these very abstract concepts and often worked on trying to define these things. But the way he thought about them were often in terms of examples. And that's actually something, when I started working with Joe, was quite alien to me. Joe had this amazing ability to come up with the right example that exactly captures and distinguishes a new definition from an old one, and makes us really understand what is going on. So I'll start talking about knowledge and then move on to causality. But really, when I talk about these things, Joe didn't just provide the seminal works. He literally wrote the books on all of these topics. This knowledge book, together with Ron Fagan, Yoram Moses, and Moshe Vardi, is the fundamental text on knowledge. And his book on uncertainty as well. And finally, his book on causality is really the one that is defining these notions and the way we think about them today. Okay, but let's jump right into knowledge. And I'm going to do this through an example. You already heard about applications to distributed computing, but instead let's focus on one example from, this is an old example, it's an old puzzle. But that was first analyzed in the work of Joe and Yoram Moses. So many of you have heard this, but if you haven't, it's a really cool puzzle. You have 20 kids that are sitting in a room, and this room has no mirrors. Here are some kids. Let's say there are 5 of them here. And some of them have mud on their forehead. Okay? This is a room with no mirrors. You can see everybody else, but you don't see yourself. So if you're this player here, you can see there is somebody else having mud on their forehead, but you don't know about yourself, right? Now, the teacher comes into the room where the kids are sitting, and he says, some kids have mud on their forehead. Okay, they already know this, right? In this scenario, there are two of them, they already know it, that some kids is not telling them something new, it would seem. And then he asks, does any of you know that you have mud on your forehead? Everybody says no, because there are no mirrors there, right? You know about others, but you don't know about yourself. Okay. Then he asks again. Everybody says no again. And then he continues asking. And after 7 questions, suddenly some kids say yes. That's very bizarre. And then the puzzle here asks how many says yes. We don't have time to wait for solutions. So I'm just going to give you the solution. You can think about it afterwards. The answer is 7. Okay. Why 7? Well, on a high level, the way you want to think about it is that if the situation had been like this, okay, so there's only one kid with mud on their forehead. Then if you were this guy here, the one with mud on the forehead, then you see that nobody else has mud on their forehead. So in that case, when the teacher says some kids have mud on their forehead, you suddenly know that you now have mud on your forehead because everybody else that you see doesn't, so it must be you. Okay. Now, if there are more kids, it turns out that since you know that nobody else said anything in the first round, there must have been at least 2. So then the second round, second question, then both of these guys would have said it. And if there are more, then after 7 questions, and that turns out to be the formal way to reason about this. The question is, can we provide a formal model that allows us to reason about this little puzzle? And indeed, the thing that makes it even more interesting is that if you modify this little puzzle just a little bit and just remove the teacher. So let's say the teacher doesn't come in there at all. Okay, what happens then? Turns out that nobody will ever say anything. Now that's shocking. Okay. The reason it's shocking is because, as we said, when the teacher says some kids have mud on their forehead, he's not telling them anything new. They already knew it, right? In this scenario, we had these 5 guys, and 2 of them have mud on their forehead. So everybody sees people with mud on their forehead. It says nothing new, yet it changes something. So how can we make sense of this? And to do that, we need to have a formal model of knowledge. And indeed, that's what Joe's work with Joran Moses did introduce this very, very powerful and very influential model. So let's jump into it and just give a high-level overview of this model. And it starts off with Saul Kripke's possible worlds model. So in fact, people had already defined knowledge before. Knowledge was single agent. And how can we define what it means to know something? Well, Saul Kripke said, let's consider a set of possible worlds. These are the worlds that you consider possible. And we say that you know something if it's true in all the worlds you consider possible. So you maybe consider this world possible, this world possible, this world possible. In all of them, it's raining in Paris. If it's raining in Paris in all of these guys, in that case, we say that you know that it's raining in Paris. Right. Okay. Now, how can we extend this to a scenario where we can have agents that can think about each other? And the way Joe did this was to say, let's consider a graph of possible worlds. Okay. Each node represents a possible world. And now I'm going to draw lines between the worlds. If in this particular world, I consider a player I considers this other world possible, I draw a line between them. And then these lines that I draw here are tagged by the players. So here and here, I draw another line and I tag it with 2, meaning that player 2 might consider these 2 worlds possible, and player 1 considers these 2 worlds possible. Okay. So now this very simple graphical way is a way now to talk about what people know and also what people know about each other. Because maybe I consider very different worlds possible and you consider possible. Okay. So these lines now are prescribing people's beliefs. And again, we can now say that I consider a player one, let's say, consider something possible if it's true in all the worlds that they consider possible. Okay, very simple and elegant way. And now we can go back and see what happens in the mother-children puzzle. Okay, so one way to represent the mother-children situation, and let's consider a scenario where we have only 2 children, would be to consider the following possible worlds. So there is the world where both kids are muddy. There's a world where one is clean, one is muddy. There's a world where one is muddy, one is clean. And then there's a world where both are clean. Okay. Let's say we are in this world where both are muddy. There are 2 players who are muddy. In that case, both players consider this world to be possible. But player 1 considers it possible also that he's clean and the other one is muddy because he sees the other guy. Player 2, on the other hand, considers either this world possible where we currently are, or the world where the other player is clean, where he's clean, player 2 is clean, but player 1 is muddy. Does it make sense?
Yes.
And now let's see what happens in a scenario where the teacher is announcing something. Okay. When the teacher is announcing that somebody is muddy, in fact, not only we get the knowledge that somebody's muddy, but since this is a public announcement, we actually get what Fred called common knowledge. We not only get that everybody knows that somebody's muddy, but everybody knows that somebody's muddy, and so on and so forth. And that means that we are now eliminating this world here. Okay, effectively, players are acting as if this world wasn't possible at all. It's no longer a possible world because after this announcement, we have common knowledge. So it must be the case that in all the worlds that I consider possible, that he considers possible, this can never be the case. And at that point, we can now see that after a second announcement, we're eliminating more worlds and so on and so forth. And eventually we'll see that after K announcements, there must have been K mother children. Okay. Now, this might seem very abstract and seems kind of obscure to discuss knowledge in such a puzzle, but it turns out that this way of defining knowledge has been extremely influential and extremely powerful, both in distributed algorithms, as you heard Fred discuss, and in consensus, but I think even more importantly, in the case of game theory and rationality. A similar but somewhat different method was also introduced by Robert Aumann, and one would argue that the Nobel Prize that went on Robert Aumann was to a large extent for his work on knowledge in games. So really this is very fundamental work. What's amazing was that originally Aumann introduced these models in order to try to understand solution concepts in game theory that we already had. And you heard some of that that Larry was talking about. But Joe took it in a slightly different direction. Not only we could use knowledge to describe and understand old solution concepts, but we can now introduce new solution concepts and better understand maybe what was called irrationality in players by discussing players' knowledge and take into account the fact that our knowledge maybe is not complete. And this led to notions such as awareness and unawareness in games that we're really just beginning to see the importance of now, and they're going to be even more important now in systems with agents. So with that, let me also mention that right after this original work was introduced, Joe really saw how important these notions were in connecting communities. They were studied in computer science, but also in economics. And then he started this beautiful and very influential conference called TARC, where he brought together the creme of the researchers in the area, from computer science, cryptography, to economics, cryptography also. And this conference is still ongoing and is now has this wonderful community of computer science, economists, logicians, philosophers, And more recently, in just the last few years, it's also starting to be frequented by psychologists and even behavioral neuroscientists. So it really shows the breadth of work that Joe's research led to. Let me move on to this second topic. I'm going to do this kind of fast, which is causality. So completely different topic now. So what is causality? Well, there are two types of causality we often discuss. One is called statistical causality, statements like wet roads cause accidents. And another one is something called token or actual causality, which is trying to answer questions like, what does it mean to say that it was the wet roads that caused Bob's accident? So Bob had an accident, why do we say that it was the wet roads that caused it? Okay. Now, like Joe often would say, why do we care about things like that? Well, here's one example from Joe's presentation. It's true that it was raining, and it's true that I was drunk, but the cause of the accident was the faulty brakes, right? And that's why I'm suing the car company now, because it was their fault. So how do we make sense of something like that? And this is hugely important in law, history, science, and most recently in computer science and AI. Why? Because we need to often provide explanations for decisions that agents are performing. Okay, why was it the case that my mortgage application was denied by this LLM? Okay, tell me the reason. And what was it that caused my mortgage application to be denied? So let's see how we can define this. This is not a new question. Joe did not introduce this. This goes back to Aristotle. And indeed, there was a classic approach. Okay, that goes back thousands of years, first formalized by David Hume in 1748, but it goes way back. Okay. And the approach is very, very, very simple and elegant. And it says the following: A caused B. If it is the case that if A had not happened, then B wouldn't have happened either. Right? Elegant, right? If the brakes hadn't been faulty, I wouldn't have had the accident because I drive very well drunk and wet roads don't matter. It was the brakes. If that hadn't been the case, that they were bad, I wouldn't have had an accident. Okay, very nice. This was formalized in logic by David Lewis in 1973 using something called counterfactuals. Actually, counterfactuals also rely on these possible worlds and models that we discussed before. Okay, so can be formalized, great. But David Lewis also had a counterexample. Okay, and perhaps that was even more important than a formalization, because it kind of broke this 1,000-year-old idea that we can define causality. And here's his counterexample. Okay. There are two friends here, Susie and Billy, and they love to throw rocks at bottles. Okay, they are now very, very good at throwing rocks. Okay, they both have perfect accuracy, but it just so happens that they're throwing rocks at this bottle, but Susie throws just a little bit before Billy. Okay, so Susie's rock hits the bottle first; it shatters the bottle. Okay, if Susie's rock hadn't, then Billy's rock would have shattered it also because he's perfect too. Okay. Now, who caused this bottle to break? Clearly, Susie caused it to break, right? She threw the rock broke the bottle, no question about it. Okay. So Susie is the cause, or Susie throwing the rock is the cause of the bottle breaking. Now, Billy is not the cause, for sure, right? Now, it turns out that this old definition going back to Hume, but for causality, doesn't work. Why? Because if Susie had not thrown the rock, okay, what would have happened? Would the bottle have broken? Sure, it would have broken because Billy's stone was right there behind it. Okay, it's true that Susie's throw preempted his to hit, but if she hadn't done it, it would have still broken. Okay, so it totally breaks it. So now we're back to zero. 2,000 years of research on causality gone, and we don't have a definition. And this is where Joe, together with Yoda Pearl, came in and provided the today standard definition of causality. Yeah, and it's actually, the high level idea is very conceptually clean and simple. To formalize is a little bit more complicated. But here's the key idea. What we say is that we're going to work with a definition of but for causality, but let's fix some additional properties of the world the same to what they are today. Okay. So let's fix the fact that in the current world, Billy's stone did not actually shatter the bottle, right? In what the world we live in, it wasn't the case that Billy's rock shattered the bottle. So let's fix that event. And in that case, if we consider what would have happened if Susie hadn't thrown, then indeed, in fact, the bottle wouldn't have broken, and therefore she would have been the cause. Now, to formalize this, you need something called structured causal models, where you describe the world through a set of variables, and these variables are connected through equations. And formally, the way they did this was to say, let's fix some variables to their actual value, the values of today. And then let's see how these equations are affecting one another once you fix those variables. And this leads to a pretty satisfactory definition of causality. There are still some counterexamples actually to theirs, much less, but it's actually still an ongoing topic for research. And for PhD students, I think this is a wonderful topic to actually think about. Yoda Pearl received a Turing Award some years ago, in large part to his work on causality, and I think that this work was really a fundamental part of that also. Today, this work on causality is also the basis, as I mentioned, for the modern area of AI ethics and definitions of responsibility and blame and intention, and they're all very related to causality. Okay, this was essentially it. I wanted to mention just one sentence on something completely different that Joe also worked on, and that is something called cryptographic game theory. Okay, had nothing to do with these philosophical questions. It's more about what does it mean for a cryptographic system to be secure. Okay, this is the area that I am an expert on. I work on cryptography, and that's actually how I started talking to Joe. I wanted to understand his work on cryptographic game theory. In cryptography, we consider security against attackers, and attackers can do whatever they want. They're adversaries. Okay? We consider security in this model where the attacker is as malicious and can do whatever he wants. And that seems to be as strong as can be. Right? After all, if a system is secure, even in the presence of an attacker, it can do whatever he wants. Then what more can we hope for? Now, since we consider such a strong attack model, we often have to make assumptions on a certain fraction of the attackers, certain fraction of players being malicious, and the rest are considered to be honest. So we have this way of grouping the players into honest players that are doing what they're supposed to be doing in the protocol, and then the malicious ones are trying to break the protocol. Now, what Joe asked was, well, you know, to be honest in a scenario like this, why would anyone be honest? What happens if they are just rational? And it turns out that this whole body of work on cryptography breaks down if you replace honesty with rationality. And the classic paradigm for building cryptographic protocols no longer works. And he had some very nice impossibility results showing that considering malicious together with rational agents, you cannot do anything. At least if you have protocols with a fixed number of rounds. And this led to this whole area of cryptographic game theory that's also become like a pretty huge area. And Joe's work was really seminal in that aspect too. To sum up, I really feel blessed and privileged to have had the opportunity to work so much with Joe. I came into Joe's office in 2006 to talk about cryptography, and in fact, I wanted to apply some notions of sequential rationality to cryptography. This notion that Larry was talking about, and I hadn't seen Larry's slide before, but that's a second paper that that Larry mentioned about non-standard probabilities. was a paper that during our first meeting, actually with Joe sent me, here's a draft of a thing that I'm working on. What do you think? And at that point, that was a 4-page draft of, and I was just, my mind was blown by this idea of using non-standard probabilities to characterize sequential equilibria. And that's the type of guy Joe was. He would never, like, he would be happy to discuss anything and share his ideas and share his draft in progress. And he was just the most humble and nicest guy you could think of. He loved apples and yogurt. And that's, yeah, despite being this giant, intellectual giant, he was still the humblest, nicest guy one can ever imagine. That's it.
Thank you, Raphael. Yes, actually, yes. Thank you again. Also, Fred and Larry, once more. And let us thank Joe. Let us thank Joe for the science, for I guess, I hope, when you leave here, you're going to be inspired by the curiosity, by the range of this, incredible intellectual. And also, I would like to thank Joe for having made this possible, being here together as a community. Let's remember this moment. We care about each other, about our ideas, and about us as people. As I don't know if any of you is a Liverpool fan, I'm not, but as they say, you never walk alone. So remember that in this department, you don't walk alone. And it's beautiful that you guys showed up for this. Thank you.